All right, today we're happy to have Priyam Patel from Purdue University. He's going to tell us about effective separability for hyperbolic and surface and three-dimensional groups.
Okay, thank you, and thanks for the invitation. Right, so what I'll start off by doing is maybe just talk about what separability properties I'm going to discuss today. So some of the stuff I might get to at the very end is joint with Khalid Bourabi and Mark Hagan. That's more on the three-manifold stuff if I get to that. So let's just start off by describing the separability properties that I'm going to be talking about. So the first definition I'll give is what it means for a group to be residually finite. Okay, so a group G is residually finite basically if I can separate any non-trivial element from the identity with a finite index subgroup. Okay, so if for every non-trivial element in the group there exists G prime, a finite index subgroup of G, that's missing this element. Okay, so such that G is not in G prime. Okay, so just the little cartoon to keep in mind here. Can everyone see if yeah, okay, good. So if this is a group G, and if I take my element little g, well, I can produce a big finite index subgroup that misses that element. Okay? The second definition I'll give is what it means for a subgroup inside of a group to be separable. Okay, so if H is a subgroup of G,
so
we...
G here is finitely generated, right? So otherwise it's not quite
Oh, it's okay. I mean, you can, doesn't have to be finitely generated for the definition, no.
Wait a second, don't you need, so to get from here finite quotient, the conjugates?
That's finite quotient. Oh, you're talking about to say separating on finite quotient rather than finite index subgroup.
Yeah, that's, then yeah, for those two things to be equivalent, yeah, so right. But this is the definition I'm going to use, actually. So I don't require the subgroup to be normal, ever. Okay? Right, so now let's take a subgroup inside of the group. We say that G is H subgroup separable. Okay? If for any element that's in G but not in H, okay, so I take an element outside of the subgroup, and I can produce a finite index subgroup that separates the two. Okay, so there exists, again, a finite index subgroup here of G. And this finite index subgroup should contain H, but not contain little g. Okay, but little g is not in G prime. Okay, and the picture here is I take my group G, and some subgroup H here, and an element outside of it. And now I can produce a finite index subgroup that contains H but not G. Okay? So that's what it means to be H subgroup separable. Okay, so whenever this is true for all finitely generated subgroups of your group, we say that it's subgroups. This group G is subgroup separable, or LERF. Okay, so if G is H subgroup separable for all finitely generated subgroups, then G is subgroup separable. Or sometimes this is called LERF. Okay, so this is locally extended residually finite. Okay, so this is extended residually finite means that we're considering subgroups. Locally here is for finitely generated. So sometimes we talk about groups being separable on different classes of subgroups like quasi-convex or geometrically finite. And then there are similar acronyms for things like that, like QSURF and GFERF. Okay? Yes. Right, so now, what I should tell you is what effective separability gets us. So when you have effective proofs of these properties for certain groups, it can lead to quantifying these properties. Okay, so what do I mean by quantifying residual finiteness or subgroup separability? Here I'm talking about actually bounding the indexes of the finite index subgroups that I'm considering. Okay, so depending on what information you're given, maybe this is in terms of data about the group, or if you're considering, like we are, the fundamental groups of surfaces and three manifolds, maybe in terms of geometric data. Okay, so I'll say that residual finiteness, so these properties are going to imply, so if you have a group that's LERFs or subgroup separable, okay, it's definitely going to be residually finite. You just take H to be the identity, right? So it's a much stronger property than residual finiteness. And in general, proving them and producing effective proofs is much harder for these stronger separability properties. Okay, so so why do we care about these properties? I think the original motivation comes from solving decision problems. So if a group is residually finite and finitely presented, it has solvable word problem. Okay, you can actually produce an algorithm then to say if a word is trivial or not. Okay. And if it's subgroup separable, you have a solution to the generalized word problem. But in our context, maybe when G is the fundamental group of a manifold, the reason we care is that there are some serious topological implications for these separability properties. Okay, so we have topological implications or interpretations for what these properties mean. Okay, and that's something that I'm going to focus on for a while in a second. But just to give you an example of something which is like a quantifying result, I'll just state a theorem to give you an idea of how these things go. So I'm going to let sigma be a compact surface of negative Euler characteristic. Okay. And I'm going to take, we'll say there exists a hyperbolic metric on sigma, okay, such that if I take any non-trivial element in the fundamental group, okay, we can produce this finite index subgroup missing alpha. Okay, so that alpha is not in the fundamental group. Oh, sorry, alpha is not in H. Okay, and where does the quantifying come in? And the index of this subgroup is bounded by 33L. Okay. Here, L is the length of the unique geodesic representative of this homotopy class of loops. Okay, so the first part of the statement is just saying, okay, well, we can always produce a finite index subgroup. That's residual finiteness. And now we're quantifying residual finiteness. Okay, you can actually have a bound on this index just in terms of the length of the element that you're trying to miss. Okay, so this is kind of...
Is sigma closed, or do you allow this?
It can have boundary, yeah, it can. Today I'm going to let it be closed just for simplicity, but yeah, it just has to be compact. Yeah, and orientable, non-orientable is fine as well. Okay, so this is kind of the general aim that we're aiming for statements like this. But for now, let me just give you a little bit of background about what we know.
So this implies that for any hyperbolic structure, there is an upper bound which is linear in the length.
Right, yeah, so if you... Yeah, so this precise number is going to come from the metric that I'm putting on it, and I'll explain to you what that precise metric is in a second. But if I change the metric, it's just going to change by some bounded amount. Okay, so let's just give some background and history. So what do we know for surface groups? Okay, so here I mean of the fundamental groups of surfaces. We know they're residually finite. This is by work of Malchev in the 40s. Okay, we actually also know that they're subgroup separable. Okay, so they're separable on all finitely generated subgroups. And this is by Scott in, I always get this wrong, 78. Okay. okay, in 78. Okay, and this is actually, a lot of the ideas that are introduced in this paper are really used to quantify and to generalize these results to three manifolds. So I'll talk a lot about Scott's work today. And what he uses here is embedding the surface groups. Maybe I'll just put hyperbolic here, because those are the ones that I care about. We're going to use here the embedding of these fundamental groups of hyperbolic surfaces into a group gamma, which is an example of a right-angled Coxeter group. Okay, and this right-angled structure, it's really important. Okay, I'm going to tell you what the gamma is in just a little while when we get to this, because that'll affect the metric that I'm putting on the surface to get this specific bound. Okay, so this is what we know about surface groups. And maybe I'll take a little more room here. So what do we know about three manifold groups? So we do know that they're, for compact three manifold groups, so these are residually finite. And this is by Hempel, and the date again is in 87. Okay, this is assuming the geometrization conjecture. Okay, assuming. The geometrization conjecture. And now we get to hyperbolic three manifolds. We now know that they're Lerf as of 2012. And this is building on like tons of work. The last piece was done by Agel. Okay, this is in his proof of the virtually Hawking conjecture. So I'll sort of explain it a little bit why what Agel proves has this, like, these are very group theoretic properties, and so we'll start seeing now the topological implications when we're saying that it implies something that's topological here in three manifold theory. Okay, and this is building on the work of Weiss, Haglund, Weiss. Okay, and I will then now say, then this is Agel, Groves, and Manning. This is the appendix of this paper. And there's lots of other names I can put here, some of which are Caligari, Gabay, Monahan, Thurston, Bergeron, Weiss. There's lots and lots of ingredients that go into proving this. Okay? But now we know that they're also Lerf. Okay, so let's focus here for a second on Agel's work. Why would something like, proving subgroup separability help you prove the virtually Hawking conjecture? So the virtually Hawking conjecture tells you that for hyperbolic, in the setting of hyperbolic three manifolds, tells you that you can produce a finite index cover that contains a special embedded surface. Okay? So how do I start seeing things like that from these group properties? So here, what Agel's proving is the virtually special theorem. Okay, so what this tells you, Agel's work tells you that the fundamental group of a hyperbolic three manifold group, and I'm going to put basically embeds inside of a group. This is a right-angled Artin group. Okay, so really I'm lying here. It actually contains a finite index subgroup that embeds in a right-angled Artin group. But you'll see the parallelism here. I mean, here Scott's producing, some special right-angled Coxeter group that these things embed in. And now this is the analogy in the three manifold case of these right-angled Artin groups. And those two classes of groups are really closely related. Okay, so let's now talk about how something like this, and using separability properties of right-angled Artin groups, right? How this is going to say anything topologically. Okay, so I'll just start off with talking about the topological implications of something like residual finiteness, and then get to something like subgroup separability. Okay, so, right, I just erased the definition of residual finiteness, but what are we looking for? I mean, basically, let's just talk about the surface case, okay? So I've got my surface sigma here, and I'm going to take a non-trivial element of the fundamental group, And maybe this is the unique geodesic representative, which I'm also going to call alpha for now. And what are you trying to do? I mean, you're trying to produce a finite index subgroup of the fundamental group of this thing that misses this element. Okay? So, the microphone. Okay. So here, I want to produce, using the correspondence between subgroups of the fundamental group and finite covers, connected covers, I want to produce a finite cover here. Okay, this is corresponding to that subgroup that I'm going to produce. Okay, and I want this thing, the fundamental group of this thing, so H, to not have this element in it. So what that means topologically is that when I lift this curve, it's actually non-closed. Okay? So alpha tilde, a lift of alpha, is a non-closed path. Okay? And this would mean then that alpha is not in the fundamental group of this cover. Okay, so that means alpha is not in H. So this is the topological reformulation of residual finiteness. You look for a finite index cover where the curve does not lift anymore. Okay? Okay, and what's the topological interpretation for subgroup separability? And this is where you start to see how these things can have an effect on getting embedded surfaces like you need for the virtually Hawking conjecture. Okay, so let's focus on this in the case. So here I'm just using the surface case. Let's just say we start off with the fundamental group of the three manifold to sort of demonstrate what's going on here. Okay, so here's your three manifold. And I'll say, suppose that we have some immersed surface sitting inside of here. Okay, so this thing bumps into itself. This is my sigma. And it bumps into itself. Okay? Here, this overlap, this self-intersection of the surface is going to be caused by, so this is caused by some element G in the fundamental group of the manifold, which is not in the fundamental group of this immersed surface sitting inside of there. Okay, so if we knew that the three manifold group was separable on this subgroup, right, on pi 1 of sigma, what I can produce then is a cover, a finite cover, so a finite index subgroup, right? So this is a finite cover, so a finite index subgroup that has the surface group but does not contain this element G. Okay, so what does that mean? What I've basically done is I've taken the thing that causes it to bump into itself and it's no longer there, so I'm resolving that singularity. Okay, so now it's nice. Okay, so here we can see how something like subgroup separability can actually help you promote immersions to embeddings in finite covers. Okay, so immersions. Immersions to embeddings. And that's precisely what we need, right? We need a finite cover of the manifold that actually contains an embedded, a special embedded surface. Okay, so so now you can sort of see how maybe, a natural question that can come up is, in the virtually Hawking conjecture, I now know that there's this finite index cover and it contains this surface that I want. Well, maybe I could ask, what's the index of that cover, right? And so to get something like an effective statement for the virtually Hawking conjecture, you certainly need to get an effective statement for these sort of subgroup separability problems, right? So that's sort of showing you the motivation, one of the motivations for doing like these effective separability things. Okay, now I should talk about really quickly like a very special case of this. So lifting immersions to embeddings. So a special case, maybe I'll put this right here. Is what if I just consider, here I'm taking the fundamental group of a surface sitting inside the three manifold. But let's just talk about like in the surface case, right? I have this curve sitting inside the surface, and it's bumping into itself. It's self-intersecting. It's immersed, right? Well, if I can separate the subgroup generated by this one element, right, from if it's subgroup separable on that, I should be able to lift this curve to be embedded in a finite cover, right? So if I can promote immersions to embeddings, right, I can do that for curves here. So maybe what I'll say is, so a special case of lifting these things is lifting closed geodesics to be embedded in finite covers. Okay, and getting an effective statement here would just mean bounding the index of that cover. So we can do this. So if we start off with the same setup, so again here sigma is a compact surface of negative Euler characteristic. Okay, then I'll say there exists a metric. Again, I'll tell you what that is later. There exists a metric on sigma such that any closed geodesic lifts to an embedded one in a finite cover. And the index of that is again just bounded in terms of the length of this element. So whose index is less than 17 L. Okay, so again, you can take an embedded, you can take a closed geodesic that's self-intersecting a bunch, and just lift it to be embedded actually. So it's there, it's closed, it's in actual loop, but it's embedded now, and the index of that cover is bounded in terms of the length of the element. Okay.
By metric, you mean hyperbolic metric, right?
Oh yeah. There exists a hyperbolic. See, I left that space there. Yeah, there exists a hyperbolic metric on here. Okay. So what I'll say is, so yeah, we're in the surface case, and so I've showed you an effective statement for residual finiteness, and this special effective statement for something related to separability. There is an effective statement for lerfness too. Maybe I'll just write that down. I won't write down the explicit bound because it's a little bit more complicated. But this is. Oh, by the way, I should say that this promoting immersions to embeddings. This is done by Scott, showed by Scott in his paper, in that same paper where he shows that surface groups are lerf. And that's like this is a really important concept. It's called Scott's criterion that was introduced then. Okay. So this is an effective statement for Scott's result on the separability of hyperbolic surface groups. Okay, such as separability. So I'm just going to say with sigma as before, and the metric as before as well. If we take a finitely generated subgroup of the fundamental group and an element that's in the fundamental group and not in S, then there exists this finite index subgroup that we're looking for, containing S but not G. Well, here I said gamma. And we can bound the index. The index of this subgroup is bounded by some explicit constant, which we can calculate. And the stuff that the constant depends on is the number of generators in your finitely generated subgroup. Okay, so this is number of generators of S. Okay, the length of those generators. Okay, and the length of this element that you're trying to miss. Okay, and what I'll say is that it's linear in these lengths and exponential in this length. Okay, so I'm not gonna focus on this today. What I'll try to do is sort of give you an idea of what kind of techniques go into the residual finiteness statement, the quantified residual finiteness statement, and this sort of quantify lifting geodesics to be embedded in finite covers. So those two things are pretty related. And if I get time, I'll also talk about maybe very briefly, some of the work that's being done for quantifying, these separability properties for right-angled Darton groups, because that's what affects the three-manifold case. Okay, but this is where we'll focus on the surface case for now. Okay, so just for convenience, what I'll say is, you don't need this, but today I'm just going to let sigma be closed and orientable. So oriented, and its genus is where you write this to. Okay, so this is just for today. Okay, so the first thing I'll do is say something about the metric. I mean, in all these statements, I'm saying there exists a metric, and obviously that metric winds up being important. So let's just start off talking about that. So remember that I said Scott shows that all of these surface groups embed inside of this right-angled Coxeter group. Okay, so what is this right-angled Coxeter group? This embedding is what's going to actually give me my metric. So the right-angled Coxeter group gamma, what we do is we first start off with a regular right-angled pentagon in hyperbolic space. P. Okay, so P is regular and right-angled. And what I'm going to do is just take the group generated by reflections in the sides of that pentagon. Okay, so gamma, this is the subgroup of isometries of hyperbolic space, hyperbolic 2 space, and it's generated by reflections in the sides of P. Okay? So that's how I produce my right-angled Coxeter group. And so of course the images of P under this group gamma tessellate the whole, this tessellates the whole hyperbolic 2 space. And what Scott's telling us here is that, I'm embedding each of these surface groups inside of this right-angled Coxeter group. So what that means is that I can produce a fundamental domain for the surface that's consisting of these pentagons, where side identifications are coming from elements in gamma. Okay? And that's the metric that I'm choosing on the surface. So this embedding gives me my metric. Okay, because I'm giving you the fundamental domain. It's the one that's a union of a bunch of these pentagons, and side identifications are coming from elements in gamma. Okay, so what does that mean for us? What it basically means is that the surface is tiled by these pentagons as well. And every cover of it is also tiled. And that's really what you should take away. So sigma and its covers are tiled by copies of P. Okay? And that sort of right-angled tessellation on the surface is going to prove to be super important for these results. Okay, so let me just put up that picture again of what we're looking for when we're doing the topological interpretation for residual finiteness. Okay, so remember that you have your surface, and what you're trying to produce, oh, the picture's here, excellent. There's lots of board space. Okay, right. So what are we trying to do here? We're trying to take this curve and have it lift to something that's non-closed in a finite cover. Okay, so I'm going to claim that what we then need to produce, actually, let's do this over there. This can be. So in order to produce something like this, what I'm going to claim is that it's enough to produce the following. So we want Y, a connected subset of hyperbolic 2 space with the following two properties. Okay, the first thing is that we want Y to be the convex union of a finite number of pentagons. These right-angled pentagons. Okay, so hyperbolic space is tiled by these. And the first thing that I'm going to want is that Y is a convex union of a finite number of them. Okay, so the picture here is Y. Looks something like this. Okay? And the second thing that, and I'll explain why we want those two things in a second. The second thing we want is that alpha tilde, a lift of this curve to the universal cover, is contained in the interior of this set Y. Okay, so alpha tilde is a lift on alpha. Here. So that's sitting somewhere in here. Why is that enough? Okay, so somehow I'm going to claim if we can get this, well, we're just going to produce the group that's going to get you here. So now I need to produce this H, right? So I'm going to let H be the group of isometries generated by reflections in the sides of Y. Okay, so if H is reflections in the sides of Y, well, this is sitting in hyperbolic space. And the sides of Y are sides in our tessellation, right? So these sides are reflections in, I mean, these are elements of gamma then, this right-angled Coxeter group generated by reflections in the sides of the pentagon. So certainly we know that this H is a subgroup of gamma. Okay? And if Y is a finite union of pentagons, okay, this Y now, by the Poincare polygon theorem, okay, this is going to be a fundamental domain for the action of H on hyperbolic 2 space. So this is why you need convexity. So convexity, this is a criteria, this is a hypothesis in the Poincare polygon theorem. And this is the conclusion. You now know that this Y, this thing that I've created, is actually a fundamental domain for the group generated by reflections in the sides of Y. Okay? And the most important thing is, since I know that this is a finite union of pentagons, well, the number of pentagons in Y is going to be precisely the index of H and gamma. So this is eventually how we're going to get an actual quantitative result, right? We need to know the number of pentagons here so we get some bound on indexes of subgroups. And what I'll claim is that that's actually going to be, whenever I produce this set, it's actually going to be proportional to the length of my curve, and then I win. Okay, so this is kind of like what we're aiming for. And so very quickly, I'll just sort of tell you how we create something like this and highlight some of the issues that come up when you're doing this.
Is that index equals the number of pentagons also PPP? The result of Poincare?
Oh, this is just because if this is a fundamental domain for I mean, gamma is reflections in that one, right? So the number of pentagons in your fundamental domain will be precisely the index of that subgroup, always. Yeah. Okay, so, right. So how do we produce something like this? Okay, so just a quick sketch. What you do is, so we want this thing to be in hyperbolic space, but where you actually work is in the cover X. This is corresponding to the cyclic subgroup generated by that one element alpha that you're trying to miss. Okay? So we're going to work in this space and sort of construct a set like this Y and then lift it up to the universal cover. Okay, so what does this look like? This is going to be an open annulus. Okay, and inside of that open annulus, this is the cover X corresponding to the cyclic subgroup generated by alpha. So again, keeping track of the blue ones that I'm looking at, this is going to be, when I look at this space sitting above the surface, there is a unique simple closed geodesic that's a lift of that original curve sitting right there. Okay, so what do we do here? I claim I want to produce this set over here. So I want to basically produce some union of pentagons here, because this thing is tiled, right? We're taking the metric on sigma with the tiling, and so every cover of it is also tiled. So we want to produce a union of pentagons in this tiled space that contains this curve on the inside. Okay, so the natural thing to do first is just take all the ones that intersect that curve. Okay, so we take all the pentagons. S is going to be the set of pentagons in this tiling that intersect this thing. And this is my set S. Okay? But that's not going to be convex, right? So when I zoom in here on this boundary, what does this look like? I mean, you've got maybe a convex corner there, right? So these are all right angles. So this is a union of right angled pentagons. So your interior angles, so this is my set S, your interior angles are either going to be pi over 2 or 3 pi over 2, right? And these are the problems. These points on your boundary, that's what's causing non-convexity, right? So this is not good. And what you can see, though, is that maybe I can just start adding in some pentagons here to fill in these non-convex parts, okay? The only fear that you have is that as you're adding things in to make it convex, maybe I don't end up with a finite number anymore, right? I just have to keep adding and adding and adding and adding, and that's not good. I want this to actually be a convex unit and a finite number of pentagons. Okay, but I'll tell you that doesn't actually happen. So you can convexify S, and I'll call the convexification of S this Y, okay? You can convexify S just by adding not that many pentagons, okay? So you don't need to add many pentagons, okay? Okay, so now what's my picture? I've somehow extended this a little bit, and it's really nice. It's convex, right? This is my set Y. Okay, but you can already start to see sort of, and I can't. This is a precise estimate, so you don't need to add too many. That's like I can tell you exactly how many you need to add, right? And you can pin down this number. And the number of pentagons in this Y is going to be proportional to that length. You guys can already start to see, how that would be. So the number of pents in Y is proportional to the length of alpha bar, which is actually the length of alpha. Okay, so doing this sort of thing, you can see how you could get to an actual quantification. Okay, and what you need to do now is lift this set to the universal cover. Okay, so we're working here. And the third part here now is to lift, right? Lift Y to Y bar sitting inside of hyperbolic space. And then I hope that I've produced something like this. Okay, with this curve actually captured on the interior. Okay, so here, again, so first I'll say to convexify and knowing that you don't need to add that many, it definitely uses this right-angled structure a lot. And the second place where you're definitely going to use the right-angled structure is in the lifting. Okay, you can very carefully lift this set. So really I'm pulling back every pentagon. Let's just say this is the geodesic axis for that element alpha. Okay, I can pull back every pentagon in the set so that if I take one lift, here, maybe I'll do it in blue. This is one lift, alpha tilde. So when I lift it up, it's really nice and convex. And this is my Y bar. Basically just cut open along the seam in the tiling of that surface. Okay, this is almost good enough, but what do we need? We need this lift to be contained in the interior, and it's not, right? So in some sense, this will be good for us when we're going to talk about lifting a curve to be embedded in a finite cover. But for residual finiteness, it's not good enough. But there's a cheap trick you can do, which is just say, okay, well, there's a neighboring lift here, right? There's a neighboring lift here. This is alpha tilde prime. And I'm just going to take the pullback of the set for that geodesic. So I'm adding a second copy of this, basically. This is Y bar prime. Okay, so now what do I have? I've got this lift, and at least one endpoint is sitting inside, and that's going to be good enough. Okay, so if we let y prime be, or y hat, let's say, be y bar union y bar prime, this is our set. This is our desired subset that we wanted over here. Okay, the number of pentagons in y hat is twice the number of pentagons in the set y, and this is still proportional to the length of alpha. Okay, and that's how you produce this actual finite cover. Okay, because this was what we wanted, and now we can project down to here, and we know the index basically. It's proportional to the length. Okay, so now one thing you might notice is, yeah, so this subgroup that I'm producing, like you do reflections in the sides of this thing. It's not a subgroup of my fundamental group. This subgroup, like H for this y hat, is going to be a subgroup of gamma. But we already know that the fundamental group of the surface is also a subgroup of gamma. So you just let H prime be the intersection of the two. And this is that finite index subgroup that you were looking for that misses the element. Okay, and I'll say again, remember, the index of this group inside of the fundamental group is now bounded by 33L. So you can actually calculate the specific number there. Okay, so this sort of shows you some of the ingredients that go into residual finiteness. So why was I saying that that other result was related? So when you're trying to lift that blue curve to be embedded in a finite cover. So now you don't want it to open up completely. You just want to resolve all the singularities. So you want it to actually be embedded. So you don't want to capture it on the interior, right? So what do you do when you're trying to lift it to be embedded? You play the same exact game, but now you want it to actually be there. Okay, so I'm going to claim that you go through the same exact argument all the way up until this step. Okay, and now at that step, what do you do? So we still produce y the same way, y and y bar the same way, lift it the same exact way. So you've got this picture where we've got the geodesic axis and one of the lifts sitting here. Okay, we've got our y. With these blue endpoints are actually on the boundary here. This is my y bar. Okay, what I'm going to claim is that if I take K to be the group generated by reflections in the sides of y, okay, and I'm going to add in the element alpha, because if I add in the element alpha, when I look at the cover corresponding to something related here, it's actually going to be there as a loop. It's not going to have opened up, right? I'm going to claim that if I take this to be my group K, that's the one that I'm going to sort of use to get to it being embedded. Okay, so let's talk about this for a second. So the first thing that I'll say is that if I look at this y bar, so we can show that this y bar is a fundamental domain for the action of K on hyperbolic 2 space. Okay, that's going to use the fact that this group breaks down as a semi-direct product here. Okay, in some sense, you can see that all the elements of alpha are going to sort of move this around along this neighborhood. And then the reflections are going to wind up filling up the whole of hyperbolic space. Okay, so you can prove this. Y bar is going to be a fundamental domain action. Okay, so what then can you see? So if we look at hyperbolic 2 space, modding out by this subgroup, okay, the interior projects by a homeomorphism here, right? And so what you're going to see is that here the curve is actually, I mean, this is sort of staying exactly like this in the surface, right? But the endpoints are actually going to be identified, okay, because at least the element alpha is in K. Okay, so that element being there means that this endpoint gets identified to that endpoint. So the loop actually lives there, but you can show basically that this is going to, I mean, of course, this is going to project by a homeomorphism to the interior, and that none of the other lifts here are really going to play a role. Okay, it's not going to be that any element in this group sort of brings this lift to another one that's crossing it, and so you actually wind up getting something that's embedded in your surface there. Okay, so alpha is in K means that alpha tilde is actually a loop. Okay, and the only subtlety, of course, is still that, like, I mean, you can make this a quick fist. This is not a subgroup of the fundamental group, but you just take your actual subgroup K prime to be K intersect the fundamental group of the surface. And I claim that, using the semi-direct product, you can basically show that because this is projecting by a homeomorphism on the interior, it's actually going to be an embedded loop. Okay, so it's just a little bit different, but it's very related to the residual finiteness argument. Okay, so that shows you just some of the techniques, at least in the surface case. And just for a minute, I'll explain to you something about the 3-manifold case. So what I wrote down before, when we're in now the hyperbolic 3-manifold case. Really, we're using now the fact that the virtually special theorem, so the virtually special theorem tells us that the fundamental group of a hyperbolic 3-manifold is virtually embedding inside of a right-angled Artin group. Okay, so the way that this is used is that we know certain separability properties about the right-angled Artin group, and then the fundamental group of the 3-manifold actually inherits those because these properties are well preserved under taking subgroups and finite extensions. So if you want to get an effective statement for separability for the manifold group, I claim that you first, you can basically get it from doing separability properties, effective separability in the right-angled Artin group, where the bound's just changing by a little bit. Okay, by some fixed constant depending on the 3-manifold group. Okay, so along the lines of getting effective separabilities for right-angled Artin groups, this is the joint work I was talking about with Khaled Bouravi, Mark Hagan, and myself. So if we take a right-angled Artin group here and an element, so this is a quantified residual finiteness for right-angled Artin groups. So if you take an element a non-trivial element in the right-angled Artin group, and its word length with respect to the standard generating set for the right-angled Artin group. If you don't know what that is, that's okay. It's just a special one that we always use. So if this is a length n element with respect to the standard generating set, then there exists a finite index subgroup of the right-angled Artin group, missing that element, and we can bound the index of that in the right-angled Artin group by n plus 1. Okay, so again, you get a result that's linear in the word length here of that element that you're trying to miss. Okay, so this is the first step in getting towards what is the actual property of right-angled Artin groups that you use. You use the fact, by Haglund, we know that they're separable on quasi-convex subgroups. Okay, so this is getting towards, a statement like that, effective quasi-convex separability for right-angled Artin groups, which would then give you an effective separability for the quasi-convex separability of the fundamental group of hyperbolic 3-manifolds. Okay, so that's sort of showing you how this fits in the next dimension up. Okay, thank you.
Any questions?
Mm-hmm.
element.
Yeah,
You know,
yeah.
the bound on the cover where the element doesn't
It-
fit the closed curve.
Yeah.
So
Oh,
do-
that's 33L, right? Yeah,
33?
yeah, that's okay.
And so do you have a feeling whether or not there exists a sublinear upper bound in
Yeah, I'm not so sure. So what I'll say first is that the bound is not sharp. It's coming from like knowing how far away these pentagons are, and then putting this inside of some neighborhood that you know the right.
Yeah, but I'm talking
Right.
about just in
Just
general.
yeah.
Do you have any intuition there?
I think it's linear,
You think it's actually linear?
but I'm not so sure. Yeah. I think it's linear. Yeah. So for the free groups case, you can get sublinear. You can get like n to the 2/3 or something like this, right?
No.
For residual finiteness.
It's something else. You're thinking about something else. I just checked while you were talking. I looked up the paper, and the best upper bound, for this problem for the free group,
It's polynomial, right?
It's actually like n over 2.
Oh, n over 2, n over 2. I'm sorry,
But
right.
it's
Not
still
n
linear,
over 2,
yeah.
still linear, right? It's n over 2. That's right.
I was very surprised.
Yeah, sorry, the
Because
lower
my intuition
bound.
about the free group is that there should
Yes,
be
yes, yeah.
sublinear upper bounds. but
Right.
apparently it's
Yeah, n
not.
over 2 is correct. Yeah. The lower bound is something like n to the 2/3. Yes. Yeah.
That's for normal.
Uh-huh. Yes, it's also for normal subgroup, right? This is for just
Yeah, probably,
yeah. It's fact checking me.
Any other questions? Well, now let's thank Priyam again.